Firstly, I'd like to thank Protochips and Ninke for the opportunity of showing our work to the public today. This work was published this year, and as the name suggests, in situ TEM as toolbox for emerging science of nanometallurgy. We are talking about a new methodology for TEM in situ experiments using then different alloying systems. To properly elucidate the topic, I'll be talking about the motivation of work, and also along with the description of methodology, results, and conclusion. As we see, as a motivation, we need to properly explain the importance of nanomaterials, and for that we need to go through three topics: miniaturization, size effect, and applications. As you see in the example of miniaturization, we have the classical phone example, in which you have the decreasing size and enhancing properties. Like nowadays we have a computer in hands, and before you had like a big phone, if you can put it like that. And that's only possible due to effect called size effect. Yeah, this size effect, as here is depicted, is actually that's one of many size effects that occur. Is the melting temperature depression versus diameter of a particle. Like in this case, our material will have so many atoms at the surface as in the bulk. Like it's so small that the surface amount of atoms is comparable to the bulk, therefore decreasing the cohesive energy of the material. As I told you right now, we have different effects. Like sublimation has a similar effect as melting temperature depression. It decreases with the size of the particle. Also decreasing, but like for instance, mechanical properties can increase. We can also change like optical properties and so on. So as you can see, you can tune our material towards our application by decreasing its size. And as an example, we can use like filters. We can have like different coatings for material, make it like hydrophilic, hydrophobic. We can have like smaller transistors, develop new materials like graphene, enhancing batteries, and so on. Like a plethora of different effects. Which leads us right now to the sample preparation topic, which is really important because we are talking right now about like a nanometric size material, which is like in the frontier of what we can analyze nowadays. Therefore, the goal of our work was to make an easier way of doing a pristine alloy sample characterization. What we mean pristine is that we're making our alloy within the TEM. For that matter, we need to start actually then placing everything together, like the material together. So for start, we actually having like in our case aluminium electropolished sample, which we like manually section it with help of scalpel. And then after that, we then separate a really small area here, around 50 micrometers, and we transfer it to a chip. This chip, by the way, was then supplied by Protochips, and it's made of silicon and has also silicon nitride coatings in our case, but can also be supplied without coating or with carbon coating. So as you see, then we transferred this 50 micrometers big piece with the help of like a paintbrush hair to the sample surface, to the area of the analyzable surface, and then we added nanomaterial there, and we hope that everything sticks together, like let's have like nanomaterial over our sample. So sample, yeah. Then after that, we went to the important part of the work, the heat treatment. The heat treatment is like three kinds of different ones. At first, as you see, like we have aluminium copper and aluminium gold systems. At first, we did a melting spike for aluminium copper at 660 degrees Celsius for 300 milliseconds. So the idea here is to reach aluminium melting temperature and as fast as enough that you don't have acidification and have like kind of the same shape of material before and after melt. It's important because if the material is periodized, you don't have electrotransparent area anymore. Hence, we don't have ways of analyzing it anymore. Then we did, like for aluminum copper system, a precipitation treatment after the melting at 460 degrees Celsius for 3 minutes, and for aluminum gold precipitation 250 degrees Celsius for 2 hours. However, it was only possible to do this kind of setup because we had, like, in conjunction with our MEMS chip, also a special holder, also supplied by Protochips, and these, with conjunction of software, allowed us to properly control our heating sequences and also make a possible analysis of our resulting outcome. Sorry. With that in mind, then we go to the results, and here for the first part we're talking about alloying. The alloying of aluminum copper and aluminum gold occur differently. As you see here, for aluminum gold, we have like a subtle transformation. We can see here like maybe that's appearing of a particle here in the middle, but it's not like striking difference in the Hadaf picture that you can see here. In this TEM Hadaf video that you can see for aluminum copper, however, is striking. After the melting occur, we have like a lot of stuff happening. But I mean, we need to be sure. Therefore, we did like an EDS before and after to compare the results. And as you can see, for aluminum copper, as it's obvious, you see here right now like some veins of copper everywhere. But for aluminum gold, it was subtle. We need to then do like higher magnification in the middle of the material to see some small plates. We didn't know, however, that if these plates were like drifted away because the aluminum melt and then push the particles apart. Therefore, we need to do, like for both cases, a heat treatment to be sure that we can make new phases out of this resulting specimen. So we then go to heat treatment. For aluminum copper, and for aluminum copper we have Hadaf video as well, and here you see then also a striking difference. Like when we reach 460 degrees Celsius, for some time we see like a bit of growth of some particles, they precipitate, so we can do a heat treatment. Hence we can see that alloying is possible. For aluminum gold, on the other hand, that was subtle. So here is the picture right after melting, and then right after the heating began at 260 degrees Celsius. The heating, by the way, was done instantaneously. We see the formation of needles everywhere, and yeah, like we see also that transformation is occurring, which is a good indication, good sign of alloying. And when we go like along, like it's like 1 hour later, we see like growth and breakage of some needles, and the same behavior is also observed after 2 hours of experiment. We also did then an EDS before and after to analyze the material composition overall, and like after melting for aluminum gold, we do have like the maximum solubility for gold in aluminum around it, and after the heat treatment we also have the same for 260 degrees Celsius. Also, after the heat treatment, we did quenching of the aluminum gold and aluminum copper as well. Here we see, like we cannot actually say regarding the EDS much because we have like a really low signal of like a little low amount of gold there in solution. But we we're lucky enough to have a particle at the whole region. And it could then there do a selection area diffraction pattern, electron diffraction pattern, and we see aluminum to gold reflexes, which are possible phases to be built in this left side of the phase diagram of aluminum gold, which is a good sign showing that the alloying was actually possible to be done in this case. It's important also to note that we also need to have our sample on the whole region, because there we can do proper like selected area diffraction pattern, because if you have like over the silicon substrate, we can then have mixed signal of the substrate as well. For the aluminum copper, we see then clearly that something was occurring. After the melting, we do have maximum solubility of copper in the matrix, and after the heat treatment as well, like we are following the phase diagram as expected. And by we found here a really good precipitate, and analyzing it, we have like the same or similar ratio like of aluminum copper to the theta phase, which would be 2, so 2 aluminum for 1 copper. And by doing a selected area electron diffraction pattern in this same particle, we see also the theta phase reflexes, hence indicating that the phase formation is respecting the phase diagram. You see then the formation of the theta phase, which is expected. So with that in mind, we can conclude that alloying was possible despite the existence of an oxide layer. The characterization of different alloys prepared with the TM is possible, and is really intriguing because right now we can actually do a pristine alloy within the TM and look there inside and see the whole transformation occurring. You don't need to do ex situ. And the size effect was not observed to hinder the alloying, but we cannot rule that out entirely because we would need then to have like maybe a better setup to properly analyze and study these size effects for this kind of setup. With that, I would like to thank you all for the attention, and if you have any questions, I'd love to answer them maybe in YouTube or email, like the way you like to answer me. Many thanks, Protochips and Nick again for the opportunity.